going to be talking about the algebraic computation of limits. During peer leading or during a previous class, you've played with limits as this idea. As I get closer and closer to some fixed a in the x space, what happens around a? What happens to y around a? Not necessarily at a, although that can happen, but what's going on just to the left and what's going on just to the right. So now that we have this kind of graphical view of limits, let's talk about how to compute limits algebraically. To do this, we're going to start with two basic functions. We'll add a third, 1 over x later. And we're going to have some limit laws. So let's talk about these functions first. Ultimately, our goal is to be able to compute for fixed a, to be able to compute the limit as h goes to 0 of f of x plus h minus f of a all over h. Or for fixed x, to be able to compute the limit as h goes to 0 of f of x plus h minus f of x over h. We want to be able to do these algebraically. Because of that, we're going to start here and build up some algebra. So let's talk about these two functions. We've got a constant function. Recall that a constant function is just something that spits out the same number every time. So for example, if I have the function f of x equals 4, well that means that whatever my input is, my output is always going to be 4. So the limit, so f of 5 is 4, f of negative 637 is 4, and f of pi, or f of the square root of 2, both of those are 4. So this function here maps everything from the x space into some particular c. And it doesn't matter what the number is in the x space. Everything gets mapped to whatever the c is. So if I'm talking about a particular a, don't care where it is, it's going to get mapped to c. But everything around it is getting mapped to c. So the limit of a constant for any real c, for any constant, and for any input a, including negative and positive infinities, what goes on around a, the limit as x goes to a of the constant c, is nothing but the constant c. Okay, so here's the graph of that. As you can see, the limit as x goes to infinity, well, I've got 4, 4, 4, 4, 4, 4, 4, on up to infinity. So the limit is infinity. Go right over here to 3. Well, what's going on around 3? Well, I'm getting back 4. So the limit as x goes to 3 of 4 is nothing but 4. Okay. The next rule we have is called the limit of the identity. Okay? For any a, for any x, including a, the next rule we have is called the limit of the identity. It says that for any real number a and positive and negative infinity, the limit as x goes to a of x is just a. In other words, I take whatever I'm going toward and stick it in at the end. Now, if you think about this function, this is called the identity function. And the reason it's called the identity function is it gives as the output whatever you gave it as the input. Okay? So here's the number 0 in the x space. Here is 0 in the y space. Okay? So 0 is going to map to 0. 1 is going to map to 1. 2 is going to map to 2. 3 is going to map to 3. Negative 1 maps to negative 1. Negative 2 maps to negative 2. Pi maps to pi. The square root of 2 maps to the square root of 2. Everything just maps back to itself. The graph of that function is right here. F of x equals x. So I give it the input 1, I get back 1. I give it 2, I get back 2. I give it negative 1, I get back negative 1. I give it 0, I get back 0. This is known as the identity function. Now, our special rule is that the limit of the identity for any a, including the infinities, is just back what a is. So if I take the limit as x goes to negative infinity of just x, well, as x goes to negative infinity, this way, y goes to negative infinity. the limit as x goes to 3 of x is simply 3. As I come over here to 3, here's my x as 3. I come over here and I talk about what's going on around 3. So I want this area and this area. Well, what goes on around 3 is 3. As I approach 3 in x, I am approaching 3 in y. So those are our two new rules, the limit of the constant and the limit of the identity. Now we need to add some theorems so that we can compute things algebraically. Okay, so the statement of the sum law is this. Let A be some real number. Notice I'm confining myself to finite things for the moment. There will be an infinite version. Let f and g be functions defined near A. If the limit as x goes to a of f of x exists, and if the limit as x goes to a of g of x exists, then the limit of f of x plus g of x also exists, and the limit of the sum is the sum of the individual limits. Now, let's do an example. Compute the limit as x goes to a of x plus 4. Well, it's rather trivial, but let's just do it anyway. The limit as x goes to a of x plus 4 by the sum law equals the limit as x goes to a of x plus the limit of x goes to a of 4, which, combining with the rules that I already have, but the limit of identity gives me this, so this first one is 8, and the limit of the constant function gives me that that second one is 4. So I wind up with 12. Now, it's important to note that I need to check to make sure I met these conditions, right? Because I sort of just applied it without really checking. I need to know that both of these limits exist. Well, this first one does exist, and this second one does exist. There they are. Therefore, this sum law was a valid choice. Okay, so now we have the limit of constants and the limit of the identity function, and we have the sum law, and we've played with an example. Now let's add two more tools to our toolbox. The first one of these is called the constant multiple law. What it says, again, another theorem, let A be a real number and f defined near A, basically how all these things start. If C is a constant, now if C is a fixed constant, not moving with the limit sign, and if the limit as x goes to a of f of x exists, then the limit as x goes to a of that constant times f of x also exists, and the limit of the constant times f of x is nothing but the constant of f of x times its limit. Now, this is a more specific application of a more. Now, this is a specific application of a more general rule. Why have this as a separate rule? Well, when we get to derivatives, we're going to want this as a separate rule. So hold on to your horses as to the meaning of why we bothered. Because the next thing we're going to do is the product law. Let A be a real number. Let f and g be functions defined near A. If the limit of f of x exists and the limit of g of x exists, then the limit of the product exists and the limit of the products is the product of the limits. Okay, so let's apply our rules in an example. We want to compute the limit, algebraically, the limit is x goes to 2 of pi x squared plus 4. So we're going to do a little algebra, break this up. You can see that this is really pi times x plus 4. We can break up the sum using the sum law, which gives us the limit as x goes to 2 of pi x times x plus the limit as x goes to 4. Let's get rid of this using the constant law, which we have from before. Break that up, that just becomes 4. And then let's pull this pi across the limit. Since pi is a constant, I can use the constant multiple law to simply pop it right off there. Okay, well, now I have these two things right here. I'm going to use the product law. The product law lets me say that the limit as x goes to 2 of x times x is simply the limit of x goes to 2 of x times the limit of x goes to 2 of x. And then I've got my baggage, the pi and the 4. So I apply the limit of the identity, since both of those are the identity function, and I wind up with pi times 2 plus 4, which equals 4 pi plus 4. Now, I know what you're thinking. Scott, do I really need to be that pedantic? Do I really have to do every single line of this? Yes, for the moment. We'll get to why we don't need to do that a little bit later. Also, notice from this example, I've got x times x. If I did this again and again and again, so if I had x to the fifth, right, I could apply the product law 5 times and simply get x, to get the limit as of x to the fifth. Sorry. So notice here that if I did that, this is the limit as x goes to 2 of x plus x. Well, if I did this again and again and again and again, if this was x to the 7th, I could have applied the product law 7 times. And I would have wound up with the fact that wound up with the fact that the limit as x goes to a of x to the 7th equals the limit as x goes to a of x to the 7th. Okay? So, we're going to have another law there. That's called the power rule. If this thing right up here is a positive integer, okay, the power law is going to say that I simply move the integral inside the power law is simply going to say that I can just move that 7 right off the top of that limit sign, and the limit of x to the n is the limit of x to the n, and that's called the power law. So let's take these new little tools out for a little spin and see what we can do. Let's get at basically any polynomial. We've got our limit laws here, our list of limit laws. Let's do an example. The limit as x goes to 2, compute. The limit as x goes to 2 of x to the 7th minus x squared plus 5x. Well, the first thing I'm going to do is apply the sum law and break everything up into nice little terms like so. Now, bear in mind, I need to be able to check back. So I need to know that the limit of x to the 7th exists, that negative x squared exists, and that the limit of 5x exists. But just keep it in the back of your mind as we do the algebra. Now, I apply the constant multiple law. This one I'm going to leave alone. This one, I'm going to pull out the negative 1 using the constant multiple law. And of course, I don't want to say plus negative 1 times. I just say minus. Plus 5. I pull the 5 across the limit sign, and I wind up with 5 times the limit as x goes to 2 of x. Now I apply the power law. Power law here says that the limit as x goes to 2, well, I just pull off the 7. So the power law says that I can just pull the 7 right out of here. And so I've got the limit as x goes to 2, whatever that number is, of x equals 7 to the 7th. Then I do the same thing here, minus whatever this limit is squared, plus, and then this, of course, is left alone. Now, I've got the limit as x goes to 2 of x, the limit of x goes to 2 of x, I got the limit of x goes to 2 of x. I can apply the limit of an identity, and I just sub in the 2. So I got 2 to the 7th minus 2 squared plus 5. Now, notice something here with this example that we just did. All I could have done, notice here, I wound up just taking the 2 and plugging it in for x here. And I wound up with this thing here. This function has something we call the direct substitution property. Okay? I could have started here by just plugging in the 2 for the x, plugging in the 2 for the x there, and plugging in for the 2 for the x there, and I would have gotten that answer. Again, this is called the direct substitution property, and this is extremely important for us. What this means is that we could make a theorem that would give us this nice little thing and make it so that we could do this from one step. That's the next goal. One step thing. If a function is like the last one, where I could have just subbed in a for whatever the variable was, we call such functions, we say both of those functions have something called the direct substitution property at a. So let f be a real function defined both at and near a. Now notice here I need it defined at. I'm not just talking about near anymore. F has the direct substitution property at a if the limit as x goes to a of f of x equals f of a, just like it did for that last polynomial. Another example of this is the identity function, which we've already talked about. The identity function has the direct substitution property. Let f of x equal x, then the limit as x goes to a of f of x. simply equals the limit as x goes to a of x, which is the limit of the identity, is simply a. So we have that the limit of f of x as x goes to a of f of x equals f of a. Okay? So polynomials are a class of functions that have what we call the direct substitution property. Okay? For example, I want to compute the limit as x goes to 1, a finite number, x to the fourth minus 5x squared plus 7. So this is a polynomial. I know it's a polynomial. I write, just sub in 1 for all the x's. 1 to the fourth minus 5 times 1 squared plus 7, which is 1 minus 5 plus 7. And I know you're dying to write that that's 3, but this is the better answer because it tells you where it came from. Okay, so we want to prove this fact about polynomials. We want to prove that polynomials have the direct substitution property because that's nice, right? I don't need to write all of these little steps anymore. I just write ds poly and I'm done. So, we're going to talk about this more in class, but I want to write a little introduction. I want to say what I'm going to do, what is it I want to show, and then I'm going to say a few words, just a few, about how I'm going to do it. So, I want to show that the limit is x goes to a. Recall the definition of a polynomial. A polynomial is a function so that there are constants cn minus 1, blah, 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 c1 and c0, so that the function can be written, there are a finite number of constants, so that the function can be written as cn x to the n plus cn minus 1 x to the n minus 1 plus blah, 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 c1 x to the first plus c naught. And I want to show that the limit of this equals this. You know, the function if I just directly substitute in. My strategy is I'm going to work backwards. Now, the reason I'm going to work backwards is because remember that there's a little condition on top of all of these. And that is that the limit, provided that the limit of this and the limit of this exists and so forth. So to be careful about that condition, instead of working from the top down, which you could, but then you'd have to go back and say, okay, yes, I got to limits that exist, and therefore this step, this step, this step, this step, and this step were justified. Instead, we'll just work backwards, and we'll start with the conditions. We'll start by doing things where we know the limits exist, apply our laws, and then work up to getting this. So what we're going to do is we're going to start from here and go here. Okay? So I have this statement. Now, by the limit of the identity, right, I could take this essentially A, and I could stick it down here, right? It's a little tricky to think about backwards, right? But what I'm doing is I'm just taking this A and I'm calling it the limit as x goes to A of x. So I'm taking this A here and I'm just calling it the limit as x goes to A of x. I'm just making an algebraic substitution there, and I wind up with Cn, the limit as x goes to A of xn, and now I'm tired of writing all these middle terms, you know that they're there. And I wind up with the last one, C1 times the limit as x goes to A of x, plus this C0, which is just hanging out. Now, I apply the power law here to stick these ends inside. Instead of bringing the ends out, I want to stick them in. Okay? Because I know that this limit exists. Therefore, I know that this limit must exist. And that these two things must be equal. So, again, I just move those ends all in, and I get this nice little statement where the ends for all these middle terms, the n minus 1, the square on the second to last term, all of these terms are in. Now, I want to put the constants in, right? And this last one over here is a nasty little sucker, okay? I need to deal with him as well, okay? The way I'm going to deal with him is the constant law. Well, C0 equals the limit as x goes to A of C0. So I'm going to deal with you here. And for the rest of these, I'm using the constant multiply law to stick this back in. Because I know this limit exists from the previous steps, I can just stick you in. Blah, 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 blah. And I get there. And then I'm going to do finite number of sum laws, okay, to just kind of combine everything together. And since this is a finite function, I can do this, right? If I get 2, then I can just keep applying it again and again and again, and I get any finite number of them. And I wind up with the thing I'm looking for. Therefore, my conclusion, so I know that the limit, since I started this way and worked this way, I know that the limit is x goes to a of this expression equals what I'm looking for, and I have the direct substitution property.